Welcome back. In this video, we will explore how objects move in circular paths and delve into the forces that influence them. During the first part of this video, we'll establish the centripetal acceleration formula, and in the second part, we'll explore various examples. We will now formulate an expression for centripetal acceleration. Imagine a point, denoted as P, situated at a distance r, from the origin on a Cartesian plane, featuring x and y axes. The point's coordinates are represented by x and y. The angle theta represents the direction of the vector OP, relative to the horizontal axis. We can illustrate vector OP, as displayed on the screen, with our hat representing the unit vector along OP. We can express the vector P, by incorporating the angle theta, and the corresponding distances along the x and y directions, as shown here. To determine the linear velocity of P, we need to find the derivative of P, with respect to time. It's important to note that vector P, is a function of theta. Therefore, we can calculate the derivative of P, using the chain rule, as demonstrated here. The derivative of theta, signifies the angular velocity, representing how the angle changes over time. However, we assume that the object's angular velocity remains constant. Hence, the rate of change of P, equals the product of the angular velocity, and the rate of change of theta, as shown on the screen. We can now calculate the time derivative of P, as demonstrated on the screen. Let's rewrite the equation in the manner shown on the screen. This equation indeed clearly shows that the velocity vector is at a 90-degree angle to the position vector. The magnitude of the velocity can be expressed as follows. Next, we take the derivative of the velocity to determine the acceleration of the object, as demonstrated on the screen. The acceleration corresponds to the rate of change of velocity, while the angular velocity relates to the rate of change of angle. We maintain the assumption that the angular velocity remains constant. Hence, we can reformulate the above equation as depicted on the screen. When we calculate the derivative of velocity, we get the object's acceleration, as shown on the screen. Let's rephrase this equation, for improved clarity in terms of direction. This equation demonstrates that the vector's direction points towards the center of the circle, around which the object is rotating, leading us to term this acceleration, centripetal acceleration. The magnitude of the acceleration is represented by the expression shown here. Let's recap what we've covered up to now. The velocity of the rotating object is at a 90-degree angle to the positional vector, as demonstrated in the animation. The magnitude of this vector is specified as shown on the screen. We maintain the assumption that the object's angular velocity remains constant throughout. The centripetal acceleration of the object is directed towards the axis passing through the center, about which it rotates. In simpler terms, regardless of the object's orientation relative to the rotating plane, this acceleration vector consistently aligns with the central axis and remains perpendicular to it. This is an important point to consider when addressing questions related to rotating objects on an inclined plane, or when the object itself is inclined to the plane on which it rotates. I hope this explanation was clear. In the next video, we will work through several examples to enhance our comprehension of this subject. Please subscribe to this channel. That will encourage me to make more and more videos on this subject. If you found this lesson useful, please leave a comment below. Please don't forget to press the bell icon before you move out of this channel. Let's meet again with another video. Bye.